Ever picked up something made of metal, like your house key or even a part of a bike, and just wondered, how in the world did this get made? Well, a lot of the time, it starts its life as just a boring, solid block of raw material. And the journey from that simple block to a super precise part, that's the art of machining.
I mean, really think about that for a second. How do you go from a solid, heavy block of aluminum to something as insanely intricate as a car engine, with all those little pistons and cylinders and channels all working together? The answer is, well, it's surprisingly simple, but it's also kind of profound.
You just carve it? Yep. You start with way more material than you actually need, and you just precisely remove everything that isn't the final part. It's this beautiful art of subtraction. And that's what we call machining.
Now, this process of getting rid of material is sometimes called wasting. And I know what you're thinking, that sounds pretty negative, right? But in the world of making things, it's actually a term for a super controlled, super precise technique. It's really the heart of what we call subtractive manufacturing.
Wasting isn't about being wasteful at all. It's about revealing a shape that's hidden inside. Seriously, think of a sculptor. They look at a giant block of marble and they can already see the statue inside. All they have to do is chip away the extra stone. A machinist? They're doing the exact same thing, just with a block of metal. They're carving away to reveal the finished part.
Okay, so let's start with the absolute fundamentals. I mean, before we get to the giant computer-controlled robots, we've got to understand the basic ways of shaping stuff that we've been using for, centuries.
First up, sawing. We all know this one. It doesn't matter if it's a simple handsaw or a massive industrial bandsaw, the idea is exactly the same. A blade with a bunch of teeth removes a tiny little strip of material, a little fun fact, that's called a kerf, to make a clean, straight cut.
But what about thin sheets of metal? Sawing isn't always the best way to go, and that's where shearing comes in. Just picture a giant, powerful pair of scissors. Tools like a guillotine or tin snips basically apply a huge amount of force to slice right through the material. It's way faster and much cleaner for that kind of job.
And then you've got filing. This is all about the fine-tuning. After a part gets cut, the edges can be pretty rough. So you grab a file and you slowly, carefully, remove tiny bits of material to smooth everything out and get those dimensions exactly right. It's all about precision.
So, okay, we can cut a piece of material into a basic shape. But let's be real, most parts need more than that. They need features that actually let them do something. And that's where we get into making things like holes, grooves, and threads.
The most basic feature you can make is a simple hole. And the way we do that is drilling. A spinning drill bit just pushes into the material, carves out little chips, and leaves behind a perfect round hole. It's got to be one of the most common machining jobs in the entire world.
But hey, what if you don't want a hole that goes all the way through? Or what if you need a little channel or a groove? Well, that's a job for routing. A router uses a spinning cutter, kind of like a drill bit, but instead of just plunging in, it moves across the surface to carve out a very specific path or shape.
And what's really cool is how these processes build on each other. Let's say you want to make a threaded hole so you can put a screw in it. It's a two-step deal. First, you drill a hole of a very specific size. Then, you take a special tool called a tap to cut those spiral screw threads on the inside. That second step, that's called threading.
So to recap real quick, you've got drilling to make holes, routing to make grooves, and threading to let you fasten things together. See? They're not just random techniques. They're the building blocks that turn a simple chunk of metal into something that actually works. All right, now let's level up. We're moving on from the basic toolkit and talking about the industrial workhorses, the big guns of modern manufacturing. These are the powerful, automated machines that shape our world with unbelievable speed and precision. First up is turning. The concept here is pretty simple. You take the piece you're working on, the workpiece, and you spin it really, really fast. Then you bring in a stationary cutting tool that just shaves off material as it spins. This is how we get all those perfectly round, cylindrical parts like axles and pins. Now, milling is pretty much the exact opposite of turning. This time, the workpiece stays perfectly still. Instead, a cutter with multiple teeth spins like crazy and moves across the surface, carving away material. Milling is incredibly versatile. You can make flat surfaces, complicated slots, you name it. And this really shows the main difference perfectly. With turning, the part itself spins. With milling, the tool spins. It's a simple difference, but it's why turning is the go-to for round parts, and milling can handle pretty much any other complex shape you can throw at it. And finally, let's talk about something that sounds like it's straight out of a sci-fi movie: laser cutting.
In this case, there's no physical tool even touching the part. Instead, you have an insanely powerful focused beam of light that literally vaporizes the material in its path. It creates these incredibly precise cuts with a super clean edge. It's just wild.
And here it is, all laid out. This is basically the toolkit that built our modern world. From a simple saw cut all the way to the pinpoint accuracy of a laser, every single one of these processes has its place. If you understand this list, you basically understand the fundamental language of how we turn raw stuff into the functional, amazing objects we use every single day.
So everything we've talked about is removing material on a scale we can see, we can touch. But that leaves us with a really fascinating question for the future, right? What happens next? What becomes possible when our tools get so ridiculously precise that we're no longer carving away chips of metal, but we start removing one single atom at a time?